Hello and happy Friday, everyone. I'm Brady Volpe, founder of the Volpe firm and chief product officer at OpenVault. And today I'm joined by the broadband legend himself, Ron Hranac, in our Back to Basics series. We're diving deep into understanding and troubleshooting SC-QAM channels using an SC-QAM analyzer. Ron's going to guide us through everything from finding the root cause of problems to understanding MER and BER readings on your meter, analyzing constellation diagrams, spotting reflections, and checking overall QAM performance. If you've ever looked at your field meter and thought, oh, cool, I always wanted to work for NASA, then today's live stream is for you. So grab your coffee, your notebook, your QAM analyzer if you've got one nearby, and let's level up your troubleshooting skills with the best in the business, Ron Hranac. Ron, welcome back. We're excited to learn from you today.
Well, hi, Brady, and thank you for the kind words in the introduction. And howdy to everybody who's tuning into this, either live or by Memorex, as the old
saying in recording.
Yeah, some people
tuning into the video recording.
Some will get that, and others will go, Memorex? What's he talking?
What the heck is that?
Yeah, us old coots will get the humor on that.
So, right. Ron, I'm excited. You got a really good presentation for us today on QAM analysis, understanding Constellation, even a better follow-up on BER, and FAC, a whole bunch of good things on SC-QAM. So
yeah, I think it's got some good high-level coverage of all those topics. And, of course, you've had a sneak peek at the slide deck already. So we'll go ahead and get this up so that our viewers can also see what you and I have had a chance to look through the past few days. So, all right. So it says I'm sharing. So let me get this up, and
shout out to Greg Van Ham there. It says it's going to be a great episode. I think it is too, Craig. Welcome to the show.
All right. Now, with any luck, there should be a slide up there with a technician holding a meter next to an open pedestal. And for those who have tuned into these events in the past, they might recognize that photo. It's been used on more than one occasion because, well, quite frankly, I think it does such a good job of showing, hey, somebody's out in the field.
Another day in the field.
Another day in the field, yes. And I stole this from somewhere. I'm not sure. I think it came from one of the vendors. So anyway, thank you to the original source for this picture, which gets used over and over again. So troubleshooting SC-QAM channels with a QAM analyzer is the subject of today's presentation. But of course, before we begin, we've got to go through some real high-level basics. For example, defining the abbreviation SC-QAM. That means single carrier quadrature amplitude modulation. And some people might ask the question, well, why not just keep calling it QAM for quadrature amplitude modulation, at least with respect to these 6 megahertz or 8 megahertz wide haystacks in our networks? And the answer is, when DOCSIS 3.1 was introduced, we now had to differentiate between our legacy QAM signals and the QAM signals that make up an OFDM signal. And yes, all those little subcarriers, either 25 kilohertz wide or 50 kilohertz wide, are little miniature QAM signals. But I'm not talking about those. We did that last time. Instead, this time I'm talking about those 6 megahertz or 8 megahertz wide QAM signals. And the differentiation here is those are single carrier QAM signals. And the OFDM signal and OFDMA signals are multi-carrier QAM signals. So that's the differentiation point there.
So the SC matters when just to differentiate between an OFDM QAM and the legacy QAMs that we're using.
Well, yeah, and the OFDM QAMs, there's lots of them, thousands in a channel. And here we're talking about one per channel. So where do these things come from, the SC-QAM channels? Well, they come from a QAM modulator or SC-QAM or edge QAM modulator. By the way, many people take the shortcut, and this has been one of my nits over the years, is they'll just call it the SC-QAM channel or SC-QAM signal a QAM. It's not a QAM. QAM is a type of modulation. So we're talking about the signal that uses that modulation. And some people also call the QAM modulator or SC-QAM modulator a QAM or an edge QAM. No, that's not right either. It is an edge QAM modulator because it's the source or the transmitter in the signal. And that gadget can be a standalone box or device mounted in the rack in the head end. It can be part of a cable modem termination system, the good old CMTS. It can be part of a cable modem. It can even be a part of your test equipment that generates, say, an upstream QAM test signal. So
Yep.
they can. That's where they.
And Sweet Lou in the chat room says, love it when people pronounce it QAM. So is it QAM or is it QAM, Ron?
Is it tomato or tomato? Take your pick. You and I have a good friend who pronounces it QAM. I pronounce it QAM,
Yep.
but there's both are correct. Take your pick, whichever one you like to use. So I don't personally have a preference on that. All right. So what the heck is an SC-QAM channel or QAM signal? Well, from the RF perspective, because I'm an RF guy, it is a double sideband suppressed carrier RF signal in which the amplitude and phase variations represent the digital data that we're transmitting. We don't actually transmit data through a cable network. We transmit representations of that data. And you can see a Constellation display over here on the right. This is just a simple QPSK, quadrature phase shift keying, which is also for QAM. And what I've got on there are some angles. I show the I and the Q lines on there, and you can see the arrows, which are vectors that represent the amplitude or the magnitude of each. So you can see that little cosine wave and a sine wave next to the two green arrows, and the vector sum of those two is the red arrow. So if we assume that the green arrows are 0.707 in length each, then the magnitude of this red one's going to be 1. So we typically normalize to 1. So there's the vector sum of those two waves, which have a phase of 45 degrees, and 0 degrees is over here off to the right. That's by convention, and it goes counterclockwise around that. So that's when I talk about phase, and I'll show you some examples a little bit later on. That's what we're talking about.
Great.
Okay. Oh, now let's look at a fun block diagram. This is something I put together years ago for a slide deck I did on digital modulation. And I use this in here. And this is a very simplified block diagram of a QAM modulator. Here I'm going to illustrate how QPSK, or 4QAM, is generated by this modulator. And as you look at this, you can be certain that there's a lot of pieces and parts that are not included, because otherwise this would be way too busy and you wouldn't be able to see anything. So what we've got are two channels in here. Going across the top is called the I channel, and across the bottom is called the Q channel. And I'll show you why they have those names here in just a moment.
And you had I and Q on the previous slide when you were showing the MER chart. So I think that kind of is, you're kind of explain what that I and Q means on this slide right here.
Yeah, we're talking about vectors and all kinds of cool stuff. But just want to have that as kind of the foundation of the discussion, because anything that can affect the amplitude and or phase of a QAM signal can mess it up and cause packet loss and all kinds of things. So you'll notice there the data is going to come in on the left side. It passes through low-pass filters, goes to a modulator circuit. There's one up on the top, one on the bottom. Those are balanced amplitude modulators, which result in that double sideband suppressed carrier RF signal. If you think of your local AM radio station, they still have the carrier there. The carrier is not suppressed, and all the information is in the sideband. So the same is true with an analog NTSC television visual carrier.
So that carrier that you're referring to, is that part of the underpinnings of what we call single carrier QAM, or is that carrier not part of what we're calling single carrier QAM?
What it is you start out, if you turn off the modulation and just have the output present, you'll have a CW carrier at the center of the channel. As soon as you apply modulation, the carrier is suppressed in the center of the channel. It's still there, but it's down, way, way, way down, several tens of dB below the amplitude of the digital channel power. But it's suppressed, and then all the information is in the sidebands. So let's take a look at what's going on here. So let's say we got this string of bits, digital baseband over here on the left, and I've just got this marked out. And understand, this is a real simplistic version. It's actually a bit more complicated than this. But we got this sequence of bits. So there's a 001, 001, 11. And you'll notice I've got the alternating one's black and the other one's red. And there's a reason for that, because they're going to come to this switch at the input to this thing. And half the bits, the ones that I've colored black, are going to go up to the top channel, that is the I channel, and you'll understand why it's called the I or in-phase channel momentarily. And the other half of the bits go to the bottom channel or the Q channel, which means quadrature channel. So there we can see what they look like. So I've drawn kind of this little diagram here that shows what those would look like. Then you got to run them through low-pass filters, because you don't want what amounts to square waves going into that modulator, because it's going to result in all kinds of distortions on the output. So we run the digital data through low-pass filters, and we get what you see up here and what you see down here. So we got the 0011 and 0101, and then those filtered data streams, baseband data streams, are fed to the input of the balanced amplitude modulators, represented by the two circles with the X's in them. Now, what you see in the center here is an oscillator. This thing just generates a CW carrier. That's it. It's at the center frequency of the QAM channel. And so I've got this little sine wave right there, and the oscillator has two outputs. Now, it could go to a splitter and from one oscillator, but I just show two outputs on this. So at the first output, it's just the CW carrier as generated. And notice it's got the exact same phase as the original oscillator signal. So we say that this is the in-phase channel, or the I channel. This carrier is in phase.
So this is the I part. When we see this on the MER, the Constellation diagram, this is the I part of the channel that we're looking at.
That's right. And then this way, it's the phase is delayed 90 degrees. So there's a 90-degree phase shift. So it's the same RF signal, but here, this second oscillator output's delayed 90 degrees. So we say that 90 degrees is in quadrature. So this is the Q channel. That's why we call it Q. So these two signals, this is a sine wave, and because this has been shifted by 90 degrees, we can call it a cosine wave, but basically a sine wave with a 90-degree phase shift. So these two go to these two modulators. So this is the feed into the modulators, and then we've got the baseband data going into the modulators, and the baseband data modulates this sine wave, and the baseband data down here modulates this cosine wave. And there's the two modulated signals, and this is in the time domain, like you'd see on an oscilloscope. Yep. So what we see here, we've got the representation of our 0101 right up here, 0101. But note the phases. So this is 180 degrees phase. This is 0 degrees, 180, 0. And down below, let me get this guy out of the way here. We've got the 0011, and here we've got 0011, but the phases are 270, 270 to represent the two zeros, and 90 to represent the ones. And that's what we get when we modulate and basically amplitude modulate this cosine wave with this baseband data. We get this. Yeah. Then we combine them in a summing circuit. Let me get back to that. Oh, I'm going to show this on here.
And still at low frequency. This is as you say, at baseband. This is not at a high frequency.
No, this is RF now. This stuff we're seeing is RF in the time domain. So this is modulated RF. So remember, this oscillator generated a CW carrier at the center frequency of our QAM channel, wherever it is.
Perfect.
Could be 600 megahertz or whatever.
Yep.
Same thing. So this is the amplitude modulated 600 megahertz as an example carrier. Down here, same thing. But I put these arrows on here that are vectors. So the length of the arrow represents the magnitude of each little signal burst, if you will, and the direction it points represents the phase. So 180 points off to the left, 0 points to the right. Remember that Constellation displays 0 degrees is off to the right, 180 is off to the left, 90 is up, and 270 is down. And then here we can see the phases, 270. We've got two of them pointed down and two of them pointed up. And then when you combine them in that summing circuit, you get this.
Wow.
So these two guys, the vector sum, so you just take these arrows and the vector sum looks like that. So assume the magnitude of each arrow is 0.707 volt, then the magnitude of the vector sum would be 1 volt. We're just normalizing it here. And here we're back to our original data stream representation, 00100111. And here there's our original 00100111. So there it is. So you've got this chunk of the RF has a phase of 225 degrees. There's a phase shift right here, but the amplitude doesn't change much. So phase shift right there. to 315 degrees. That represents 1, 0. Then there's a 180-degree phase shift here. That gives us this guy here, which represents 0, 1. And then a phase shift right in here, which represents 1, 1. And you'll notice with QPSK, we have 2 bits per symbol. So each little burst of RF with a given amplitude and phase represents, in this case, a 2-bit symbol. So that's it in the time domain.
It almost seems too simple that we put ones and zeros in and we get our QAM channel out.
Yeah, this is the QAM channel. This is what the QAM channel, the haystack, would look like on an oscilloscope, just like this. And there it is on a spectrum analyzer. Exact same thing. So this is a QPSK signal right here at the output. So there's our QAM haystack. And the same thing is true for 16 QAM, 64 QAM, 256 QAM. It just the whole process gets more complicated than what I've shown in this diagram. But this helps to
the modulator gets a little bit more complicated.
Yeah, this is the modulator. Yeah, it's a little more complicated, but this is what's going on. And now that you can see that the data is represented by amplitude and phase variations at RF, if there's anything in the signal path that affects the phase or amplitude, it's going to mess things up. And that's what we use the QAM analyzer to determine if any of that stuff got messed up.
Now, it's going to mess things up when you try to receive that signal and demodulate the signal. That's what you're talking about in the signal path, right? When on the receiver side, you have basically a corresponding demodulator that's able to receive that signal. So that's what we're going to look for next, right?
It does. I don't have a diagram of the receiver, but it's basically a mirror image of the QAM modulator. It's just backwards from that. The gazintas comes out and then it's split 2 ways into the I and Q channels, and we get our bit streams and so on. So it's kind of backwards from what the transmitter was doing. Cool. So let's do a hypothetical out in the field, and this is one that may be all too familiar to many people. So let's say there's a symptom. Customer calls up. They've complained that there's intermittent tiling in some of their digital video channels, and you do a little check and you check your list and say, oh, all those digital video channels or signals that they've got intermittent tiling on are all carried in the same CTA channel. In this case, we'll say channel 88. That's a center frequency of 609 megahertz. So what's the first thing we do? Well, we might look at it with a signal level meter. So that's shown on the left. So it's measuring the signal level. And let's just say we've got a spectrum analyzer with us. So we're going to look at the QAM haystack right there. And we look at it and say, well, what do these two things tell us? Well, the digital channel power, the signal level, is plus a little over 6 dBmV. And that's actually pretty good.
Pretty good power.
Yeah. The haystack looks okay too. You don't see anything popping up out of the top of it. And
it's nice and flat.
Nice and flat. Looks, close to the same level within a dB or 2 of the other channels. So we
should be good, right? We can we can go on to the next ticket.
No, there's still intermittent tiling. So what do? Well, this must be the set-top box. No.
We can't just replace the set-top box and fix the problem.
That's what happens sometimes.
All too frequently.
Just replace the set-top box. But you don't know. You can't tell from this what's going on inside the haystack. So the signal level meter and a regular spectrum analyzer are valuable tools. I mean, we've been using them for decades in our networks, and they are extremely important tools. But they don't tell everything that's going on in that SC-QAM channel, and whether it's downstream or upstream. They tell part of the story, but not the full story. So what we need to do is have a way to look inside of that QAM haystack and see what might or might not be amiss. And the tool, of course, is the QAM analyzer. Some people call it a digital signal analyzer. But these instruments have been around for quite a few years. What was it? The Huck CR1200, I think, was the first one that I remember that the industry had access to.
It came in a little Pelican case, a little yellow-orange Pelican case was the first one that I had seen.
That's the one I remember, too. But a QAM analyzer can provide all kinds of information. It depends on the make and the model. Some makes and models support different features and functions, and others add more features and functions. But it all depends. But typical functionality includes the ability to measure things like a regular signal level meter does. So you can measure the signal level of analog TV channels. You can measure the signal level of your digital channels. That is the digital channel power. Some instruments allow you to display the constellation, which I find to be very useful. Most all of them will report the RX-MER. They may just call it MER, but it's actually receive modulation error ratio, RX-MER. Most of them for the The SC-QAM channels will report pre and post FEC bit error ratio. That is forward error correction. And many of them have an adaptive equalizer graph, so we can do some additional troubleshooting by looking at that. Now, some instruments also support other features like frequency response. They can derive the adaptive equalizer's frequency response and spit out a plot of, some people call it in-channel frequency response, but it's not the full channel. It's not even the frequency response of the network. It is the frequency response of the equalizer. And that's important to know. And that can tell you that there might be a problem with the frequency response in the plant if the equalizer's response is all messed up. They can often provide or report group delay variation, ingress or interference under the carrier, which is a powerful tool in the instruments that support it, upstream transmit level, things like upstream packet loss, ping, throughput, latency, jitter, and maybe other features I don't have listed here. So these are pretty powerful boxes that allow some pretty sophisticated troubleshooting out in the field and can really help to nail down what the problem might be.
Absolutely. And especially powerful if you understand how to take advantage of those features.
Oh, big time, big time. Here's a very simplified block diagram of a QAM analyzer. The data, actually the RF comes in on the left. So we've got a connector over here that takes the feed from the cable system, and it has what amounts to an electronic switch here. So if you're doing signal level meter measurements, then the RF is routed from the input connector to the signal level meter, which has its own circuitry and functionality that's tied into the CPU that controls the box and the display you get, the memory that's being used, keypad, and maybe an Ethernet connection. If you're doing QAM analysis, then you're essentially dealing with a cable modem or a cable modem equivalent. And the RF then goes through a diplex filter because the odds are pretty good that QAM analyzer supports upstream stuff. So you've got to have a diplex filter in there to separate the low return or the sub-split or mid-split or high split, depending on the instrument. Then the high-pass filter gives us the downstream stuff. So you got a tuner, a QAM demodulator, which is a very sophisticated circuit in itself, all on a chip. That ties to the MAC, which also ties back to the upstream transmitter, and it ties to the CPU, and then the display and memory, keypad, and all the other pieces and parts. So that's kind of the high-level overview of what's going on under the hood of your QAM analyzer. So let's take a look at a couple screenshots. These are older instruments. Some on the who are tuning in may recognize some of these screenshots from instruments they've used in the past. But I like these because they show a couple good examples. First of all, we've got a 64 QAM Constellation display on the left and a 256 QAM Constellation display on the right. But as you look at the screenshots, there's other stuff in there. They're the Constellations. So you can see the 64 QAM Constellation on the left, the 256 QAM Constellation on the right. The instrument may show things like channel number or center frequency or some other identifier. So you can see here's the digital channel frequency, center frequency. Here it is up here. Might show what it is, like symbol rate. So this shows symbol rate. This says 264 QAM. But you can look at this and see pretty obviously that it's 256 QAM. This shows the channel bandwidth is 6 megahertz. Shows signal level, minus 3 dBmV, RxMER. This one shows RxMER, pre and post FEC bit errors, and so on. So there's all that really cool stuff. So there's the pre and post FEC BER. You'll note the one on the left's got some pre and post FEC errors. The one on the right doesn't. So that's telling. RxMER, both pretty good. The 64 QAM signal's got just under 34 dB RxMER, which is really good for 64 QAM. And over on the right, you've got just under 36 dB reported for the 256 QAM signal. And now some operators have higher targets than that in their networks these days. Maybe they target 38 dB or 40 dB RxMER, but whatever it is. But these instruments show that value, which is nice. Now, going back to that one on the left, I mentioned there were some pre-FEC and post-FEC bit errors.
On 64 QAM, no less.
Well, yeah, and you look at this and you say, well, what might be going on to cause pre- and post-FEC bit errors? The Constellation looks good. The digital channel power is good. It's minus 3 dBmV, so that's fine for 64 QAM, and actually it's fine for 256 QAM. RxMER is good at almost 34 dB. Constellation looks good. But the presence of pre- and post-FEC bit errors suggests there's something amiss, but it's intermittent. And it might be sweep transmitter interference. It could be downstream laser clipping. It could be a problem with the source, the QAM modulator, maybe a loose connector or intermittent connection in a combiner somewhere or out in the field. The point is, it says, yeah, we got a problem, but you can kind of narrow it down to the class of impairments that can cause the pre and post fact bit errors, but don't affect the MER, but don't affect the signal level or aren't affected by the signal level. So this really helps us in our detective work to
Right, because an MER of 33.7 for a 64 QAM signal would, really kind of tell me that initially I would think that's pretty good.
Yeah,
the MER should be great for a 64 QAM channel, but the fact that we're getting pre and post BER kind of paints a different picture. That puts me into this, well, I can't really trust MER to me be my single metric to say, is my QAM channel good or not? I really have to look elsewhere.
Well, and an important point about RxMER is the way it's computed in a QAM receiver. It is averaged over a large number of symbols.
Yep.
So if you've got just intermittent bit errors occurring, that's generally not going to show up in the MER number that's reported by the instrument. But I know in years past when I would visit cable systems, if I was just doing some routine testing in their head end, looking at the input to the downstream laser or the input to the combiner, I'd see if I saw bit errors, but everything else looked good. First question I asked was, do you have a sweep transmitter? Yeah, we do. Is it turned on? Yeah, it is. Try turning it off for a second. Let's see. So they turn it off, and the bit errors would invariably go away. And it's okay, what you got to do is configure your sweep transmitter so you're not sweeping through your digital signal. So that was a pretty common problem early on when people were starting to roll out digital signals in their networks. But it's those kinds of things that you look for.
Yeah, I think the important takeaway is RxMER is a great measurement. It's a great metric to have and look at, but it shouldn't be the only metric you should look at.
No, it's not the only one. It's a valuable tool, and you can determine a lot of things with it. But just looking at the number itself doesn't tell you what's causing it to be the value that it is. And that's something that needs to be understood. All right, which, of course, is a nice segue to RxMER. It's a good way to characterize modulation quality. And if you look at this constellation graph here, this is just a representation of a 16 QAM constellation. And to simplify, or at least to illustrate the concept of what we're going for here and trying to determine modulation error. And I'm just looking at one symbol point up in the upper right quadrant here. So we've got the target symbol. That's this kind of dark red line here, the vector, going from the origin of the constellation out to the ideal spot. That's our target symbol. That's the ideal thing we're transmitting, and that's ideally what we want to receive. But in reality, we get what is this black vector, and that's considered to be the transmitted or received symbol. And you might say, well, how could it be the transmitted symbol? Well, if there's a problem in the signal source, it may be doing this before it even gets out that connector.
It missed the target.
Yeah, it's missing the target. And the difference between the target symbol and the transmitted or received symbol, keep in mind this could be the received symbol out in the field someplace. The difference between the two is represented by this little red arrow here that's called a modulation error vector. That's that little guy right there. And there's this little simple formula up here. The modulation error, this guy here, simply equals the transmitted symbol, or the received symbol. That's this guy, the black one, minus the target symbol. That's this kind of darker red one.
It's basically the delta from where we wanted to be to where we actually ended up.
Well, and what you've got this modulation error vector represented by this vector right here, but there's also a phase angle difference from that too, which that comes into play elsewhere. All right, so when we look at a quadrant on a constellation and we let the QAM analyzer sit there and just plot received symbols over a period of time, let's say it just does it for a couple minutes, you get this little cloud of symbol points. And I just drew it on here as a cloud. So we're looking at this, and we've got our average symbol power, which is represented by this, in this case, this black arrow going from the origin to the ideal point, which is where it should be. But it's kind of fuzzed out or spread out a little bit because of the usual noise and other stuff that's in the signal path between the source and our QAM analyzer. So what we're concerned about here is the average error power represented by this little red arrow And this is going to help us to determine RxMER, which mathematically, and this is the very high level simplistic viewpoint, is 10 times the base 10 logarithm of the average symbol power. That's this long black arrow right here. The angle represents the angle from here to here represents the phase, and the length represents the magnitude. So we've got average symbol power divided by average error power. That's MER.
Simple.
Well, sort of. And I'll show you the real formula that the computation inside the QAM Analyzer uses. But if we have a large cloud of symbol points all spread out like this, that means low RxMER. Not good. Now, I didn't draw them over on the others because if you had it here, you'd have them on all the others too, but I just drew it here to keep it simplified. If you got a small cloud of symbol points, that means high RxMER. That's what you want. A high means a big number. That does not mean high does not mean bad RxMER. High means good RxMER, like 35 dB instead of 25 dB. So here you can see things aren't spread out very much. This is good. This is what you want. There's the formula used to compute RxMER in a QAM receiver. And believe it or not, it's mostly the same as this simple one down here. We've got MER, that's MER here, equals 10 times the base 10 logarithm, 10 times the logarithm of parentheses, 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 parentheses. Then there's a fraction in there. And up here, we've got the average symbol power, but this is all of them in the entire constellation, all of them. And then down in the bottom, we've got the average error power. That's all of them for all the symbol points in the entire constellation. So you take this number, divide it by this number, take the logarithm of that ratio, multiply by 10, and you get the RxMER. And that's how it's computed inside your test equipment, inside your cable modem, inside your set-top box. This is what it's doing, is calculating this value using this formula right here. So
now, Ron, on your top constellation diagram, you show one of the symbols has actually moved into the outer boundary there, into another constellation quadrant. What happens if that event actually occurs? A symbol doesn't fall into the right boundary, into the right quadrant, constellation quadrant.
Hopefully the forward error correction can fix that, but if it can't, then you have a FEC error, an uncorrectable FEC error.
Uncorrectable error, yeah, okay.
Yeah, lost packet. This diagram I created. Actually, all these diagrams I created in I think it was for that digital modulation slide deck that I did years ago, and I had some examples that showed that you got this guy off here, you get a bit error. Whether it's correctable or uncorrectable depends on whether the FEC can fix that. Because if there's too many of them, it can't. That's the issue. And I've got a screenshot later from a real QAM analyzer that shows some of those that are spread out from the ideal point. That suggests that, hey, you got some FEC errors going on here.
We have a comment from Peter Whitman. Peter, welcome back to the show. He says, my observation, the latest handhelds, which leverage a cable modem silicon for downstream SC-QAM measurements, lacks the features of the equalizer tap view, group delay, and frequency response views. He says for the upstream, SC-QAM and pre-equalizer data is used, but for the SC-QAM downstream, it seems the EQ data is not really available. And maybe that's why you're not seeing some of that functionality in some of the newer meters, Ron.
Well, that's it. It's the functionality is there. I mean, it's built in because as he rightfully notes, the meters incorporate typically a DOCSIS 3.1 silicon, and all that stuff is going on under the hood, but whether it is displayed is up to the function feature set that the vendor of that test equipment supports. Yeah. Some instruments might support using that and letting you see it, and others might not. And my personal preference is that it's nice to have access to that kind of information because you can really tell a lot more of what's going on. And some boxes are set up to give you a green light, red light, and the green it's good, red it's bad. I like to know why it's green, why it's bad, and all those other things that may not be visible. Can be helpful. And in particular, the downstream equalizer frequency response and the downstream equalizer graph, group delay variation, those are all, in my opinion, really useful troubleshooting metrics. But,
I totally agree. I mean, the more functionality, more insight you have, the better.
Yeah, big time. All right, so kind of wrapping up the RxMER part, basically RxMER is a measure of how spread out or how fuzzy the symbol points are in the constellation. That's what it's really telling you. So a lower RxMER number means the symbol points are spread out more, and a large RxMER number means that they're not spread out as much. They're much closer together. So and the latter is what you want, of course. All right.
Agreed.
So speaking of spread out and low RxMER, here's an example. I'm using here a 64 QAM example because it's easier to see the 64 QAM information than it is on 256 QAM, simply because they're so close together in 256 QAM. And forget it on 4K QAM. It's just like a big fuzzball or fuzz box. But here you can see that the Constellation display is showing that the symbol points are spread out. And you can also see that's indicated by virtue of the fact that the RxMER is low. It's about 23 dB. So that's not good. And you look at the prefect BER, you've got some prefect errors, but there aren't any postfect errors. And this tells me that we're right on the threshold of this thing going into the dumpster real fast. We've got prefect bit errors, no postfect bit errors, so the FEC's able to fix the errors, so you don't have any packet loss. But I would venture a guess that another half a dB to a dB of additional degradation is going to start showing post-FEC bit errors and then packet loss. So you look at this display and you say, well, what's going on? And this is where you put your detective hat on, because there are a variety of things that can cause the symptoms you see here. It could be low or poor carrier to noise ratio. Somewhere in the plant prior to the connection where this meter is being used, there could be low signal level somewhere in the signal path, although you look at the signal level here and it's actually good, -1 dBmV, that's fine at the input to the meter. But there could be low signal level somewhere else in the plant that's causing degraded carrier to noise ratio, which of course could trash the RxMER. There could be excessive noise-like distortions. Maybe an amplifier is turned up too high on its output, and the noise-like distortions are causing this spreading in the RxMER. Maybe it's group delay distortion, a type of linear distortion, and you can't see that on a spectrum analyzer. And it's perhaps the group delay is so severe, even the adaptive equalizer in the QAM receiver can't fix it or compensate for it. Maybe there's ingress. Perhaps there's an improperly set up amplifier. And this is a notorious one that makes me gnash my teeth and pull my hair out, is when people will get amplifiers from the vendors who have configured these things with certain values of pre-stage, interstage padding and equalization, if equalization is used. That's done to come up with an optimum trade-off between distortion and noise performance. And many people will go in there, well, I'll say not many necessarily, but some people will mess around with interstage padding, and if there's equalization, mess around with interstage equalization. And they set up the output so it looks good, the input looks good, but the interstage padding is wrong. And what happens is the amplifier goes into distortion internally, and it generates distortions. And if you look on a full band capture display where there's a spectrum gap, you'll see an elevated noise floor in the spectrum gap. And that's kind of like a noise power ratio measurement, and it's telling you you've got distortions that are out of whack in that amplifier. And using your full band capture, you can find out where that's occurring, and then go back and then realize, oops, somebody messed up interstage padding, and now that amp's generating distortion. So, and it could generate a Constellation display that looks like what you see here. Yeah. Linear distortions, as I mentioned, group delay variation is one of those. Amplitude, ripple, and tilt's one. Reflections, all those are types of linear distortions, and they can cause things like this too. And so often I'll hear techs say, well, the MER is low, so I'm going to check for noise under the carrier. Well, noise looks good, so it's not the carrier to noise ratio. So what is it?
Yeah, but I think it's a nice, or such a difference on this particular screenshot where you have really low MER, but really very few uncorrectables, versus the previous screenshot in 64 QAM where we had decent MER, like 33 dB MER, but we had uncorrectables. And I think that's really important for people to understand, where again, MER is a great measurement to use, but you still have to look at facts to see if those uncorrectable facts are impacting this subscriber.
Yeah, and there's no post-FEC bit errors here.
Yep.
On this particular instrument, this is what it would show. It would just say less than 1 × 10⁻⁹ if there are no post-FEC bit errors. That's what it showed. So
Yeah.
we've got prefec errors here, but no post-fec errors. So that's important to understand. But again, this points you kind of down the path of different things to check that could be causing the problem.
Yeah, to
Now
your
this,
point on the turning up the amplifiers, Bill Navier says rule number 3: turning the amp up won't fix the issue.
no, don't turn it up to 11. Stop that.
Yes, even if it goes to 11, that doesn't mean it's better.
Don't do that. Don't do that. Fix the problem. Fix the problem.
Great reference there too, Ron.
All right. Yes. Some people will get that and some
Yes.
won't. Anyway, all right. Phase noise. This is a problem in the signal source, like the transmitter or the QAM modulator. If there's an up converter or down converter stage in the signal path, phase noise can occur there. And it can also occur in the receiver. Phase noise does not occur in the coax plant. This is not something that's caused by an amplifier that's misaligned or excess noise in the plant or ingress or anything else. This is in an active device, the transmitter or modulator. The receiver can do this, and any place where you've got RF up conversion, RF down conversion.
You're not going to fix this in the home.
No, you ain't going to fix this in the home unless it's the device itself. This could be occurring in the CPE. So if you hooked up your meter to the, of course you wouldn't see it if it's occurring in the customer's CPE. It's not going to show up in your meter. But more often than not, this is going to be an issue at the headend or hub site. That's the vast majority of the time. And I use 64 QAM here because it's way easier to see. And it looks like the Constellation is trying to rotate. But in this case, you can see the level's good. People look at it and say, wait a minute, what's this dBUV? Look at the channel bandwidth, 8 megahertz. Look at the symbol rate, 6.875 megasymbols per second. This is a European 8 megahertz wide Annex A signal. The dBMUV, that's 0 dBMV. Over in Europe, they use dB microvolt instead of dB millivolt. So 60.1 is 0.1 dBMV.
Yeah, we got some listeners in the chat room who definitely understand microvolts, and Bill, he got the Spinal Tap reference. So,
oh, good. And RxMER is in the dumpster. It's under 21 dB. So this is not good. This is not good. All right, now here's one you're not likely to see in today's QAM modulators. This is a signal source problem. It's called IQ imbalance. This was a problem that could occur in the very first generation QAM modulators that use discrete components to generate the signals. These days, it's all done in chips, so you're not likely to see this. But look closely at the Constellation. Note that it is narrower than it is
tall. Yep.
Yeah. So this is a gremlin in the transmitter. If you've still got old first generation QAM modulators in use and you see something like this, it's time to replace that thing with a modern box. Come on. You don't need that old first generation box from probably back in the 90s maybe.
Yeah, but the reason we have screenshots like this is because some of those boxes are still out there.
Yes, unfortunately they are. Because I thought about this. Do I include this? Because I probably should, because there may be some small systems somewhere that still use first generation QAM modulators, and they might see this and say, "What the heck's going on?"
They're around.
That's a signal source issue. All right, now this isn't any active device issue. Gain compression. Look at the outer corners of the Constellation display. They're being squeezed in toward the center of the Constellation. So we've got gain compression going on. This is just about getting to the point of clipping in the device, whatever it is. It can be a downstream laser. Yes, you can have clipping in the downstream laser, an amplifier, a node, or some other active device. But gain compression says you're kind of on the edge of things. Now the FEC is locked, but there aren't any pre or post FEC bit errors, which says it's not the clipping hasn't started yet. We're not seeing these guys start to push into the next.
Not exceeding the boundary.
No, we're not exceeding the boundary. But this says, hey, there's an issue going on there. Better find it and fix it. But at least you know what it is. And this can occur in any kind of active device through which the QAM signals pass. All right, here's an example in the upstream. This is upstream laser clipping, 16 QAM. Look at this. Notice how that the outer corners are being pushed in toward the center. RxMER not bad. It's 27 dB. Don't have any pre or post FEC bit errors, but I think if the total composite power was cranked up much more, this guy's going to start. It's going to start clipping big time, and you're going to see pre and post FEC bit errors. And this is in the upstream. So you can see that there'd be a potential issue there. So that's the onset of gain compression in the upstream. Coherent interference. This was
Donuts.
Yeah, donuts.
Love
This is
donuts.
almost impossible to see on a 256 QAM constellation because the decision boundaries are so close together. But with 64 QAM, it's really evident, and you can see the donut shapes to the symbol points on there, and that's caused by an in-channel interferer, probably a CW carrier,
Yeah.
and it creates this donut-like appearance. And note that there are pre and post-vec bit errors going on here. RxMER, for 64 QAM, we like that up above 30 dB. Probably, we saw some previous examples where it was 33 dB or higher. Here it's down in the mid 20s, so we're not doing real well on this. So this could be an indication of in-channel ingress, but CW carrier type ingress typically. All right, here's another impairment. Not going to see this, generally speaking, on modern QAM modulators, but it is a signal source issue. This could occur on one of those early first-generation QAM modulators that use discrete components. And note that the constellation is no longer square. It is kind of like a parallelogram.
Tilted.
Yeah, well, it's tilted this way, and it's tilted in the I-axis and the Q-axis, both. So that's a signal source issue. And here, the QAM receiver can't even lock to the FEC. The FEC won't lock, so you can't get any indication of bit. No. RxMER, about 25 dB, not very good. But you look at this display and say, okay, it's time to replace that old first-generation QAM modulator with a new one, because this guy is not doing. This is a signal source issue. This won't happen in the coax plant. All right, here's the zoom function that's available with most instruments that support a Constellation display. This is 64 QAM, but here we're zoomed in on one of the quadrants. It's on the downstream. And this we touched on earlier, where when you start to get some of these symbol points that start to appear just in spots where they shouldn't be appearing, then you start to get pre and post-vec bit errors. So we've got post-vec bit errors, which says we've got packet loss. RxMER is not bad. It's almost 35 dB. But look at this. The Constellation points mostly are pretty small. This is good. But look at all these little guys here that are going all over the place, just kind of randomly. That says we've got an intermittent issue, like a loose connector, or laser clipping, or sweep transmitter interference, or something like that.
Bursty noise, right? That could cause that.
It's bursty, and it's happening intermittently, and it's not happening enough to affect the RxMER. So you would look at this and say, well, MER is good. It is, but you've got pre and post-vec bit errors here.
And this, this would cause pixelization in your video. It could cause breakup in your voice calls. It would impact your gaming experience. But, you would look at MER and say, well, everything's fine. But the subscriber would still be complaining depending on how bursty that noise is and how frequently that bursty noise is coming in.
Yeah, and the signal level might be good too. And you say, well, what's going on? Signal level's good. RxMER is good. But I've got pre and post-vec bit errors, and you look on the Constellation display and you can see what's causing those pre and post-vec bit errors.
There's something under there.
There is something amiss, yes. All right, this is from the old Sunrise AT2000 series. I love that box. I think VX has got a comparable box now. QAM analyzer, spectrum analyzer, but here you can see things look good. Got the equalizer graph. Up at the top, there's the frequency response derived from the equalizer, nice and flat, group delay variation down here. And you look at that and say, well, that doesn't look good, but understand that we're just talking a few tens of nanoseconds peak to peak here. So this is actually very good group delay variation. Constellation, this is 16 QAM. This is in the upstream for both of these. And look, the symbols are nice and small and tight. The RxMER is really good at 28 dB. No pre or post-vec bit error. So this is good. This ain't.
Yeah, that's bad.
But you see the equalizer graph, you can see an indication of a reflection.
Yep.
You can see amplitude ripple in the equalizer frequency response, group delay variation. Well, we got group delay ripple, and it's not a square wave. It's just gone beyond the display setting on the instrument here. It just looks like this huge sine wave on here, but it's so the peak to peak is so bad. It's just So there's definitely a gotcha going on here. And then you look at the Constellation display. This is in the upstream. This is from a real cable system that I visited years ago. The Symbols are spread out, which suggests low RX MER. And you look over here, 21 dB. Yep, not good. No bit errors yet, but we've got this nasty reflection in here that's causing degraded RX MER. So that's something we want to get out and fix. Now, we look a little more closely at this, we can get a couple ideas to help us with the troubleshooting and say, all right, I see this reflection over here. It's offset in time to the right of the main tap on there. So it's at about 2.5 microseconds, roughly 2,500 nanoseconds. So you can do just some top-of-mind guesstimates on the length of the echo cavity just by assuming a nanosecond per foot for the time it takes RF to go through a piece of coax. So you take 2,500, the 2,500 nanoseconds, divided by 1, that is 1 nanosecond per foot, then divide that by 2, and you get 1,250 feet. Ballpark, real rough ballpark.
So we've been using digital taps in the downstream to find echo cavities the same way that we're using digital taps in the upstream in pre-equalization analysis for PNM. Yes. So this isn't anything new. We've been doing this for a long time.
Long time. This goes back, I think I took these screenshots back in the 90s.
Yeah, so long before we were doing PNM.
Well, yeah, and this the actual propagation delay through hardline coax with a velocity factor of 0.87, which is pretty common, or a velocity propagation of 87%, is 1.17 nanosecond per foot. So you just remember that number. So you got 2,500 nanoseconds for the reflection delay. So take 2,500, divide by 1.17 nanosecond, then divide that by 2, and you get 1,068 feet for the echo cavity length. And you can kind of validate that by looking at your amplitude ripple down here. And when you do that, the ripple spacing is 400 kilohertz. And you can use that formula, 492 times velocity factor divided by the ripple spacing in megahertz. So we've got a velocity factor of 0.87, which corresponds to a velocity propagation of 87%. The ripple spacing is 0.4 megahertz, so 400 kilohertz. So we're going to put 0.4 megahertz, so 0.87 divided by 0.4. Multiply that by 492, we get 1,070 feet. So look here, we got 1068, here we got 1070. So that tells us that the length of the echo cavity between two impedance mismatches is a little under 1,100 feet. And you can look on your design maps and say, hey, that's between a line extender and an end of the feeder. Maybe the terminator failed at the end of the line. Who knows?
Go fix it.
But you go fix it. But you've got this to help you out. Some QAM analyzers would calculate that distance for you, so you didn't have to go through the mental mathematics. And here you can see just down there, 252 feet for this point right here. So some instruments would provide that calculation for you, which is kind of nice. All right, operational RF levels. We can't forget signal level. In years past, when we had a mix of digital channels and analog TV channels, we typically set the 64 QAM signals 10 dB down from analog visual carrier levels, and the 256 QAM 6 dB down. And if you still use those ratios in your outside plant, even though you may no longer have analog TV channels, you want to make sure that those levels those ratios are maintained throughout the network. I know some operators, when they got rid of all the analog channels, bumped up their SC-QAM channel levels by, say, 2 or 3 dB. And they were able to get away with that and not have any issues. But whatever that ratio is, make sure you maintain it throughout the network. That's an important point, and just helps to ensure that you've got correct signal levels everywhere. Now, this is a feature in meters that I love. It's called QAM ingress. This was on a JDSU. I forget which model this was, but the meter essentially mathematically removes the QAM haystack from the display. It's actually displaying something called error vector magnitude, but it lets us see the noise floor underneath the haystack. And if you look at this, there's a couple things that it shows. First of all, where the marker is, that's this vertical dashed line, the carrier to interference ratio is about 48 dB. That's right here. So let's take a look. Remember earlier I mentioned that an SC-QAM signal is a double sideband suppressed carrier RF signal. There's the suppressed carrier right in the center of the channel. Don't think of that as distortion or something you need to troubleshoot. You'll never find it because this is supposed to be there. That is the carrier.
That is the SC part of our SC-QAM, right?
Yes, that is the carrier right there that has been modulated. But because of the balanced amplitude modulator used in the signal source, it suppresses the carrier. So there's a little bit of it still left, but it's still there. So don't try to troubleshoot it. There's our carrier to interference. There's some intermodulation distortion, about a half megahertz up from the center frequency. Then we got all these other guys. This particular system still had analog TV channels. So you can see composite triple beat right there. And some composite second order shows up there and could potentially show up here and here. And we've got the intermod up here. But this is the suppressed carrier. So that's supposed to be there. So don't troubleshoot that. So that's one way. All right, here's a screenshot from my drop about a week ago. I just used my phone and snapped a screenshot off of a Viavi One Expert and looked at a group of SC-QAM channels in the downstream. And here you can see the haystacks up here on this part, and here you can see what they call the spectrum/IUC display, ingress under the carrier or under the channel. And there you can see things look good. There's no indication of LTE ingress or other ingress in my drop, which is the way it should be.
Great feature.
And then got a couple more displays here as we get close to the tail end here. Left side is a screenshot from a system that's got a problem. And you look at the channel view up here, you can see amplitude ripple. So there's an impedance mismatch or mismatches. There's a pretty significant amount of negative slope here. And you can look at this one SC-QAM channel. In this case, it's 495 megahertz or channel 69. It's showing up as red, probably because the parameters in this meter have been set such that if it's below a certain value, hey, go out and find out why. So it's minus 8.5 dBmV. Not bad. 36.8 dB RxMER. Maybe those are below the pre-programmed thresholds in this instrument, but they're telling us, hey, there's something going on here. So go out and find it and fix it. Here's an example in the center of just kind of normal negative tilt that you might see at the end of line or at the end of a long subscriber drop. Signal level's good, minus 2 dBmV, RxMER almost 42, no pre or post effect bit errors. And then over on the right, I just did a screen photo with my phone of the One Expert about a week ago of my drop. You can see the downstream looks good.
Nice and flat.
Nice and flat, relatively flat. Levels minus 5.5 dBmV. And somebody said, well, why is it low like that? Well, I put a two-way splitter behind my modem. So
does the cable operator know about that?
Yeah, I think so. That means that the input to the modem is also going to be the same as what you see here. It's going to be about minus 5.5 dBmV. But it's fine. RxMER, look at that. Almost 43 dB. No pre or post effect bit errors, which is nice. All right. Some QAM analyzers support upstream packet loss measurements. Wonderful feature.
Yes.
They'll report it in either the raw number of lost packets or a percentage. Ideally, you don't want any lost packets in the upstream, but if you're going to have packet loss, you could live with up to about 1% for just normal data transmission, because retransmission will get the missing stuff through. But if you're doing voice, you want probably 0.1% or less, so no more than about what you see in the lower right here. All right, doing some troubleshooting. Let's imagine a scenario where you have got a widespread problem. So the suspicion might be maybe it's in the head end. So you'll go to the head end or hub site. You check the CMTS. You look at hopefully you've got a test point at or near the CMTS downstream output or the QAM modulator downstream output. So you check things there. You look at the signal level, the digital channel power. Look at pre and post effect BER, RxMER, the Constellation if your instrument supports it. Maybe some other stuff. Then check at the input to the combiner. If things are good at the output of the CMTS, but not good at the combiner, maybe you've got sweep transmitter interference or loose connections or something. If it's bad at the output of the CMTS or QAM modulator, that says probably the signal source. All right, so now let's look at the input to the downstream laser. So we're going to hook up a QAM modulator to a test point here, maybe also down at the node output. So if you've got bit errors at the downstream laser input here, but
we got a problem. We shouldn't have any in there.
Well, you shouldn't, but if they're not at the CMTS output, but you got them at the laser input, sweep transmitter interference, loose connections, combiner problems. If things look good at the input to the downstream laser, but you've got bit errors at the output of the node, could be a node issue, but it could be downstream laser clipping. Don't rule that out. It does happen. When my cable provider launched DOCSIS 3.1 in my node service area several years ago, I hooked up my meter and looked and said, oh, cool, there's the OFDM channel. And I looked at the SC-QAM channels. All of them were red, every one of them. And I looked and said, so I looked at them, and every one had prefect bit errors. No post-fect errors, just prefect bit errors. So I suspected maybe a little bit of clipping going on in the laser because of the total composite power had increased with the addition of that OFDM channel. So I contacted friends of mine who work for the cable company, and they said, "Oh, thanks for letting us know," because they didn't get any reports since there's no packet loss.
Yep.
So they checked it. A couple of days later, called me back, said they had to replace the laser because my guess is they couldn't tweak the levels to get the total composite power spot on with the existing laser. So they said that we had to replace the laser, and I checked, and everything was nice and clean. But that was something that showed up after the fiber link. I'm node +3, but I'm sure they look probably okay at the input to their laser, and the problem was the clipping going on there.
Yeah.
All right,
Should be perfect going into that laser, and ideally, really, really perfect coming out of the node if we're dealing with digital nodes today, DAA nodes.
So let's assume you're doing the troubleshooting, you're continuing, everything looks good at the output of the node. So go to the affected subscriber's premises or maybe a nearby tap. Check things there. So is it good or bad? If it's bad there, but it's good at the node, go to the halfway point and then continue to do the divide and conquer technique, although you could use a PNM tool that might help you do the same thing. But if you're doing manual measurements with your field meter, you're going to want to certainly measure RF signal levels on your analog and digital channels, RX, MER, BER. If you can, look at the Constellation, equalizer graph if the instrument supports it, equalizer frequency response, and so on. Upstream transmit levels and packet loss, if your instrument supports it. But all good troubleshooting tools to help you narrow down the problem. So wrapping up, here's a measurement and troubleshooting summary. Constellation display can provide all kinds of good stuff. You can really discern a lot of things from the Constellation display, like degraded CNR or low RX-MER, phase noise, the things we looked at, the IQ imbalance, the good old donuts in the Constellation display caused by it's interference, gain compression, laser clipping, sweep transfer interference. You can see that in the Constellation display. Pre and post effect bit errors. Well, sweep transmitter interference, laser clipping, loose connections, low RX-MER, maybe low CNR, possibly degraded distortion performance at an amplifier. Equalizer graph lets you see reflections. And then linear distortions, that's our reflections and amplitude, ripple and tilt, and group delay variation. That stuff will show up on the adaptive equalizer graph, the equalizer's frequency response, and of course a reported group delay variation if your meter supports it, the Constellation display and the RX-MER, very valuable. But all of this together really helps to narrow down what the cause of the problem might be. Transient impairments, that's that bursty intermittent stuff. Look at your pre and post effect BER. Look at the Constellation display with the zoom function. Now, of course, when you get up into the world of 1K QAM and 4K QAM, that's going to be real hard to see that because those.
And I think transient impairments are probably the most difficult ones to troubleshoot when they're in the plant.
Oh, they can be, yes. Upstream packet loss. So these are all capabilities that many of these instruments support. And then, of course, signal level problems. You're looking at things like the analog TV channel signal level. If you have analog TV channels, digital channel power on your digital signals, upstream transmit level, and then look at the Constellation display. So that's a whole bunch of stuff, which takes us to the Q&A part.
Yes. Good content, Ron. We had a comment from Peter Witten when you were going over the dB microvolts. He said, we can't handle the negative numbers, therefore we use dB microvolts. And I appreciate that, Peter, because it sure makes software programming easier. And I'm also one, I really wish we had the metric system in the U.S., so I miss that. You get to...
Yes, and I have to agree with them. The dB microvolt is easy because you're largely dealing with positive numbers.
Yes.
But I live in the world of both, having worked overseas and worked domestically. So got to remember, okay, add or subtract 60 to get the one that you want. But yeah, I understand Peter's position on that.
And Bill commented when you were, I think when you were on the AT2500, he was commenting on his Blonder Tongue BT analyzer was a godsend. I don't think I ever had a chance to use the Blonder Tongue analyzer. Ron, did you?
No, I didn't. I've used several of them over the years. All the variations from JDSU and Acterna and Viavi, and the different makes and models. Sunrise Telecom, VX. Who am I forgetting here? So I've used most of those over the years. But the Hawk CR1200, of course,
Yes.
going way back to the very first one, and I mean, just really powerful tools. They just give us so much information and allow us to really troubleshoot a lot of problems.
Yeah, I still have an AT2500 sitting just over my right-hand shoulder here, and then I think for AT2500, for people that are looking for, who really want to get into constellation analysis or anything like this, I know both VX and Viavi make larger meters that really focus on spectrum analysis or the constellation analysis and stuff like that. So like you said, I don't see it as much in the handheld meters. I don't know if that's a feature that can be added in through a firmware upgrade, but I think it's a great feature.
I think it's a powerful tool, and I wish more of the meters had it. Of course, the question is, are the techs in the field using the Constellation display versus looking at the numbers? And
I think it's whether you've been trained or not.
Well, there's the training part, but then there's, all right, how fast can you make the measurements, and what do you do? What do you use? Well, signal level, RX-MER, pre and post FEC BER, those kinds of things. But in my mind, it sure is nice to be able to see the Constellation display and the adaptive equalizer graph and frequency response and group delay variation. Those things can really tell a lot.
Agreed.
But they require training to really understand that stuff.
Yeah. Fortunately, I was trained young by people like you on using Constellation display, so I kind of grew up on it and used it for my own troubleshooting purposes, and I like it. I think it's a great feature. I think you did a great job in a presentation going over it and showing some of its value, so hopefully people find value in it. So thank you so much, Ron. That is a wrap for today's deep dive into troubleshooting SC-QAM channels with a QAM analyzer. Huge thank you to you, yours truly, Ron, for sharing your decades of knowledge and making constellation diagrams feel a little less like rocket science for everyone. And of course, a huge shout out to Mia Calabrese, who's behind the scenes, herding cats, juggling our schedules, and
she's our boss.
Yes, exactly. And making sure these shows don't turn into a QAM constellation of chaos. So
yes, that's right. Well, thanks everybody for tuning in, and enjoy your time out in the field. Hopefully, the information provided in today's presentation will help you in your troubleshooting.
Yes. And Bill says rule number 1 is if it's not working, don't mess with it. Rule number 2.
If it is
if it is working, yeah. Don't mess with it. Rule number 2, never change anything on Friday. Rule number 43, if you amplify tiling video, you'll get amplified tiling video.
I love it. I love it.
Great way to end it up. Peter says thanks to Ron and Brady for this 101 for SC-QAM measurement. Thank you, Peter. Thanks for everyone for joining in the chat room. Take care, everyone. So long.
Cheers.